Welcome everyone. Today I'm going to present our work on recognizing human action from privacy-preserving lens. Nowadays, the abundance and growing use of smart devices are causing a social dilemma. We want this intelligent system near to assist us in our activities, but we also want to ensure they protect our privacy. For decades, cameras have been engineered to imitate the human vision system, and the lenses are designed to remove aberration or defects on their surface so they can form a sharp image. Also, computer vision algorithms are always constrained to be optimized using high-quality images as input. Therefore, traditional computer vision systems could lead to privacy issues if an adversary could access to the acquired videos. In contrast to traditional cameras, in this work we learn to maximize the aberration in the lens to obtain a highly degraded image and protect privacy. Specifically, we learn to modulate the light to acquire a distorted image using a face mask such that the learned distortions preserve relevant features for activity recognition. Our proposed framework consists of three parts: the optical component, the action recognition component, and the adversarial component. We train the whole framework adversarially such that the robustness of our proposed privacy-preserving lens is improved at each step by backpropagating the gradients from the action recognition and adversarial branches to the camera parameters. Let's first zoom into the optical component. Our optical component consists of a camera with two thin convex lenses and a face mask between them. We parameterize the face mask with Cernic polynomials, where each polynomial describes a wavefront aberration. During the optimization, we learn the coefficients alpha. The face mask we learn modulates the light to encode human actions, features, and produce visual distortions. In our adversarial training, we define the loss function for our optical component using the structural similarity index measure as shown in the equation. Since we encourage distortion in the camera, this loss will be minimized. Now let's zoom into action recognition component. We can use any pre-training network to perform human action recognition. Also, we use the standard cross-entropy function as the classifier loss. On the other hand, since our degradation model could make lost temporal information, we propose to use temporal similarity matrices as a proxy to keep the temporal features similar after distortion. To do so, we build a temporal similarity matrix from the original and private videos and compare their structure using the mean square error. Finally, let's zoom into our adversarial component. In this work, we define the adversarial attack as a multi-label binary classification problem. Specifically, each video frame has one or more private attributes including skin color, face, gender, nudity, and relationship. Therefore, we train a convolutional neural network that takes a private video as input and tries to identify the corresponding private attributes. We also use the cross-entropy loss function to train the attribute estimator network. Algorithm 1 summarizes the proposed adversarial training scheme. For each epoch and every batch, we first acquire the private video with our camera. Then we update the parameters of the optical, action recognition, and adversarial component respectively at a time while freezing the other parameters. In our experiments, we use the following datasets and metrics. Here we show some simulation results of our method. The second row shows the original videos from HMDB 51 without privacy protection. To further validate our method, we built a proof-of-concept optical system in our lab in Colombia. Here we show some experimental results on acquired videos in our research group. Thank you for your attention. For more details, please visit our project webpage and read our paper.